Hello guys, today we'll take up another very interesting topic, that is superacids. And through this session we will define what is a superacid, we will see how to prepare superacids, and finally we'll see some applications. So let's get started. So first of all, the definition. Well, an acid which is stronger than pure sulfuric acid is called a superacid. So the definition is pretty straightforward. An acid which is stronger than pure or 100% sulfuric acid is said to be a superacid. Now, let us head to the preparation part. Well, the preparation of superacids involves a very simple principle. All you have to do is bring two components together and that will yield a superacid. So let's take a look at these components. So in order to make a superacid, you need two components, one of which is a strong acid and the other component is a strong Lewis acid. So when you mix up these components, we arrive at superacid. So let's take some examples to better help understand this concept. So the first such example is taking the strong acid hydrofluoric and mixing it up with a very strong Lewis acid, SbF5, antimony pentafluoride, and this gives rise to HSbF6, that is fluoroantimonic acid, and this is the strongest known superacid so far, with an acidic strength which would easily be 10⁻16 to 10⁻18 times more than that of sulfuric acid, depending on the proportion of HF and SbF5. The next such example is when we start with fluorosulfonic acid, FSO3H, and add to it antimony pentafluoride. And in this particular case, we end up with a very interesting compound which is called magic acid. This is one of the earliest known superacids which was created by George Pola and his team, and with very interesting properties. The third example, we can start with sulfuric acid, which also is a strong acid, and add to it a strong Lewis acid, sulfur trioxide, and this results in H2S2O7 oleum, which is also a superacid. And we can take one more example. So if we take HF and add to it boron trifluoride, so we end up getting HBF4, so fluoroboric acid, and this is another example of a superacid. So these are certain examples which should have pointed out to you the general principle behind creating superacids. So you need to start with a strong acid and add to it a suitable strong Lewis acid, and this combination results in the formation of superacids. Now it is time to head to applications. Well, superacids have found applications in some very interesting areas, most of which are related to research work. And the first such application is study of carbocations. As we are very well aware that carbocations are inherently very unstable species and have very fleeting existence. However, when we take superacids and prepare carbocations in superacids, so these carbocations have a long lifetime, long half-life period, and therefore making it possible to study their behavior as well as their reactions and interactions with other molecules. So the study of carbocations. So let's take an example here. So if we start with tertiary butanol and add it to a superacid, the result is tertiary carbocation, and water is removed from this particular chemical by the superacid, And the thing is that this particular carbocation is stable in superacid as a medium, enabling therefore the study of this carbocation and its interaction with other molecules. So this is the first application area, which is study of carbocations. Now let us go to the second area of interest, which is cracking hydrocarbons. Well, traditionally, cracking of hydrocarbons was done by merely using heat. So heat or thermal energy was the primary reagent which was used to crack hydrocarbons. However, superacids have found very interesting applications in the sense now the cracking of hydrocarbons can be done much more easily by using a superacid as a catalyst, and this requires much less amount of thermal energy. So let's take an example here also. So if you start with neopentane and add it to a superacid, this results in fragmentation of this particular hydrocarbon, which is essentially cracking, and we end up getting a tertiary carbocation plus methane. So this is the result of addition of neopentane to superacid with a little amount of heating, and the result is a tertiary carbocation and methane. So as you can see, a large hydrocarbon has yielded a smaller hydrocarbon, and essentially this compound has been split into two parts, which is nothing but cracking the hydrocarbon. So this is second area of application, and now let us visit the third area of application, which is creating exotic species. Well, superacids have found this very interesting applications because of their immense strength to protonate other compounds or even other elements. We can create very interesting species. For example, xenon, which is traditionally not thought of as a base, has been protonated with superacids, and the result has been a very interesting species, which is protonated xenon, XeH+. So this is another area of interest as far as superacids are concerned. So this is a very dynamic area, superacids, and it is very quickly evolving. With this, I would like to conclude this session with the promise of continuing with super bases in the next session. In the meantime, please feel free to leave your comments. Thank you.